So welcome to this economics-based session with Dr. Julia Shvets, who is a fellow in economics at Christ's, who we're very pleased to have with us this afternoon. As ever during this session, you can put your questions and things into the chat. So do pop them in there. We'll also be using polls a little bit in this as well, so you have a bit of opportunity to use those, but they'll just pop straight up on your screen. Should be pretty straightforward. And as ever, if you're having any problems, then just drop me or Lizzie a message and we will deal with those as they come through. But on that, I'm very pleased to hand it over to Julia.
Ellie, thank you very much. And thanks everybody for coming. My name is Julia Shvets, and I'm an economist, a senior lecturer at Christ's College. I want to talk to you today about economics. I love my subject, but I came to study it and later to work in economics almost by accident. When I was your age, I didn't really know what economics was. It was one of those boring words in the newspaper that meant nothing. I knew I liked two things. First of all, I liked maths quite a lot, which is something that I think you and I might have in common here. I wasn't a mathematical wizard, not like Roald Dahl's Matilda, who could multiply 13 and 379 in her head. No, nothing like that. But I was pretty good at it, and I liked it. The other thing I liked was reading. I liked to read a lot and to think about the characters in books and what made them tick. I really like to think about human beings. But when I started the university, I wasn't too sure what I could do with those two things and where I could be headed. Although I was born in Russia, I started university in the United States, where their liberal arts system allows you to choose and pick different subjects. So I started choosing and picking, trying this and that, and sort of stumbled into an economics class. And that's where my first professor of economics, Professor David Witten, showed us how to use mathematical models to think about human beings. So this was microeconomics class, and I found this fascinating, the idea that you can combine maths and try to use it to understand human beings, and I've never looked back. So today I'm going to try to give you a taste for what economics is like and what it is that economists do. But first of all, let me ask you, what do you think economics is about? So if you use the chat function, just type one word, the first word that comes to your mind that you think captures what economics is about.
Well, if you want to pop it in the chat and not the Q&A, they're two different things.
Excellent. I can see money and money again with a question mark. Anything else? Behavior. Great. Financial markets. Excellent. So economics is indeed about all of these things. Money is probably something that people most often say economics is about. If you ask a typical person, I'm very pleased to see that somebody says scarcity and incentives. Excellent. So I'm going to suggest to you guys that economics is about cake. Or rather, the fact that we cannot have the cake and eat it too. So indeed, economics is about scarcity, and the fact that, or at least for me, the main thing about economics is a study of trade-offs. So the fact that we have to make choices all the time because of the scarcity of resources, that we cannot have everything we want in unlimited quantities. And because almost everything in life involves a choice, a decision, a trade-off, going to university, deciding what's for dinner, choosing a boyfriend, this means that economics is everywhere, and it can help us understand how people make decisions. So how do economists try to understand people's decisions? Well, the first thing they use is maths. How do they use maths? They try to build what we call models. What do I mean by a model? Well, it's a formal mathematical theory that is a simplification of reality, which allows us, nevertheless, to learn something about reality. It crystallizes the statements of cause and effect for us. It isolates the factors that really matter, and it generates some empirical predictions, which we can test on data. So this all sounds a bit grand. Let me give you a very simple model of a model, an example of a model. So this will obviously be familiar to a lot of you. This is just the London Tube map. Why is it a model? Because it is a representation of reality, and yet it is a very simplified one. If we focus, for example, on the circle line, which is this yellow thing, and by the way, it's not circle at all, right? It looks like a bottle that is lying on its side. It's a very neat little bottle on the picture, but in reality, of course, circle line has a lot of twists and turns in the topography of London. Why is it not on the map? Because those details don't matter for the things that the map is useful for. It doesn't matter that the circle line twists and turns in order for me to answer the question, what's the best way for me to get from King's Cross to Earl's Court? So here is a nice model, which is a simplification of reality, and yet it does something very useful. We try to do the same in our models. So what we're going to do with you today is try to build a mini model together. Now, in order to start building a model, we need to have a problem to solve. Just sitting down and saying, I wonder how I could model behavior of people is an impossible question to answer. It's too big. So we need to start with some specific problem. And that's where I am going to come in and tell you a story. Have a look at this picture, guys. This is the United States in 1960s. Can I ask you, is there something that strikes you as wrong in this picture, at least by our modern standards? Use the chat box again to write what you think is sort of very clearly by our standards is wrong with this picture. And I don't mean the hairstyles, all right? So something here jars with us when we look at it. It's not like what we have in our society at all. Any thoughts? Don't be afraid to throw any ideas that come to mind into the chat box. There isn't a gap between the two front seats. Great, the front seats don't look like we normally expect them to see. So we're getting close, we're warm. So what else about those seats that looks so unusual? Excellent, excellent. No seat belts. There are no seat belts. There is no way that a woman in our day and age could sit like this in the car because the seat belt would restrain her. There are no seat belts in these cars. And in fact, that was the situation in the US and in Britain as well around 1960s. The cars were made without seat belts. Seat belts were not mandatory until in the United States, in 1966, a law was passed, which was called National Traffic and Motor Vehicle Safety Act, a big name, which basically demanded that all cars have to have seatbelts in them. A similar development happened in the UK at the same time, but we're going to focus today on the American story. This law was passed by the Congress and the Senate, and in those documents, engineers made predictions about the effect that the seatbelts are going to have on our lives. The main variable they were concerned about is the death rates. Obviously, this is the big thing, right? So they predicted, the US National Highway and Traffic Safety Administration predicted that death rates should go down by 13% as a result of the US passing this law. The US Office of Science and Technology predicts 14% reduction in death rates. Interesting, useful numbers. Let's fast forward a few years. Once the seatbelts introduced, people started measuring death rates and tried to see whether these predictions were borne out in reality. But when they tried to actually find out what was the effect on death rates, they found no reduction. The effect on death rates of having seatbelts was zero. What happened? How did the experts get it so wrong? Here, it's going to be useful to remember that the predictions about the death rates were made by engineers. And that's where we're going to come to a difference between the approach that an engineer takes in this kind of question and an approach that an economist would take. Engineers' approach was, don't worry about people, ignore them, they don't matter for answering this question. So we're going to assume that the same number of accidents are going to happen as before. The probability of the accident is the same, but we know that the seatbelt is going to help people in the case of an accident. So every time there is an accident, fewer people are going to die. Since we're keeping the number of accidents the same, we're going to have a reduction in the death rate. That was the engineer's approach. The economist says, let's also think about what people might be doing in the meantime. In fact, the probability of an accident depends on people's decisions. And people's decisions, for example, how fast to drive, how focused to be on the road, they might depend on whether they're wearing a seatbelt or not. I'm guessing that some of you already know what I'm trying to get at. When people have a seatbelt, they may respond to it by driving differently, and therefore change the probability of an accident, which will in turn translate into effect on death rates. In particular, it could be that people drive more dangerously when they have seatbelts, and therefore we may not have as much of an effect on the death rates as we expected. So let's see whether together we can build a mathematical model that helps us understand this kind of intuition and see whether it is actually plausible. I'm going to here build on a simple model proposed by Sam Peltzman in the Journal of Political Economy in 1975. And together, we'll start developing it by first thinking about the assumptions that we want to introduce into this model. Remember, the assumptions are these things where we simplify the reality. we're going to say these things are going to matter to us and these things won't, so we won't be thinking about them. And that's the most important decision that the modeler has to make, which things are important and which things are not. Let's first of all think of a driver. Let's call him Homer, nice Greek name. And let's assume that he drives to work every day. Once he's left his house, he has m minutes before he gets into the office. So here's our first assumption. Notice we don't really care about the rest of Homer's day. We're just going to zoom in on this one particular time of his day when he drives to work. So he has a total of m minutes available to him. That's his resource. He's going to spend some of this time driving. We're going to denote the time he spends driving by little t. And the rest of the time, the difference between m and t, he can spend in a cafe near his office. So whatever he has m minutes, whatever he doesn't spend driving, he can, if he doesn't spend all of them driving, he can then go to the cafe, get a latte, get a newspaper, and relax for a bit before he goes into the office. We're going to make some assumptions now about Homer's preferences. First of all, we're going to assume that Homer doesn't really enjoy driving. He just doesn't care about it, but he really likes his time in the cafe. So for him, it's really important to have as much time as possible with his latte and the newspaper before he faces the day. Let's continue building our model. Now we're going to make an assumption about what is the decision that Homer is making here. Remember, we want to model the driving decision and the sort of safety decision. So we're going to think about Homer as choosing the speed with which he is driving. And because the distance to work is fixed here, it's the same thing as if he was choosing the time t that he spends driving. So the faster he drives, the smaller is t. So in order not to introduce a new variable for speed, we're just going to focus on Homer actually choosing t. How long does he drive for? The faster he drives, the more dangerously he drives, and the slower he drives, the less dangerously he drives, but he spends more time on the road. Now, we're going to introduce the trade-off, because remember we said economics is about the fact that almost all decisions involve trade-offs. And the trade-off is we're going to describe it as a tension between a benefit on one hand and the cost on the other. So what's the benefit to Homer? It's the benefit of speeding to Homer is more time in the cafe. Remember, we said that's what he really likes. He wants to arrive early to have his latte in the newspaper. Let's just assume that his benefit from the time in the cafe is just proportional to the time he spends there. So it's some constant b, a positive constant, times m minus t, which is the time he spends in the cafe. So that's his total benefit. Let's now think about the costs. Well, the cost of speed is what's important for us is the probability of an accident. There may be other costs of speed, but maybe he gets caught and gets a ticket, but it's not of much interest for us in addressing our problem. So we're not going to develop a model that way. We're going to focus on the potential accident as a cost of speed. And the first thing we want to think about is the probability of an accident. And that's going to be a function of t. So how much time he actually chooses to spend driving. Remember, the faster he drives, the less time he spends driving, and that's going to affect the probability of an accident. So now, I'd like you to think about what kind of function, mathematical function, should we pick to best describe the probability, how the probability of the accident depends on this variable t? Ellie, would you mind putting up the first of the polls? So what I'd like you to think about is there are 4 choices here. A is p equals to t squared. B is p is 1 over t. C is p equals to a minus ct, where a and c are positive constants. And D is p equals a plus ct, where a and c are positive constants. Tell me which of these functions you think describes our situation better. Excellent. So I see people choosing things. Excellent. Ellie, can everybody see the results, or is it just me?
You can see it for now, but I can share the results with the group at the end, or like when I close the poll.
Yeah, that would be excellent. Thank you. So I can see people are still voting. Remember, t is the time that Homer takes to drive.
I'll give you another 20 seconds. Don't worry if you're not 100% sure.
Absolutely.
Ten seconds.
Great. So the winner is D, and we have B and C tied for the second place. So my answer here would be B. So well done, those of you who have identified B. So why B? Remember, t is the time that Homer spends driving. So the longer he spends on the road, the slower he's going. So the lower should be the probability of an accident. So we're expecting a negative relationship between P and T. This rules out option A and option D, where P positively depends on T. So we're then left with B and C. I must say that the choice between B and C wasn't easy because both of them exhibit this property that P falls with T. However, B is better for us because what we want to have is that as T grows very large, P approaches 0, because you cannot have negative numbers, you cannot have negative probabilities. And that's what option B gives us. It was a little bit tricky because in order for option B to be viable, we needed to assume that T is actually greater than 1, because if T is smaller than 1, then the probability becomes bigger than 1, and we don't understand what that is. So that is one difficulty with option B. And this is, so if an economist picks this function B, they would have to then add this assumption that T must be 1 or greater. Well done, everybody, for trying. I know it's very hard to just jump in and answer these questions just like that. Right, moving on with our model. What we've done with you is we started talking about the trade-off, we talked about the benefit, we started talking about the cost, and the cost is the accident. And the accident has two bits in it. First of all, we have the probability of accident, but we also must talk about how much damage will there be if the accident happens. And for this, we're going to introduce a new variable, which we're going to call capital L for loss. So the total cost to Homer will be a multiplication of the probability of the accident with the size of the loss. Or because we assume that the probability is equal to 1 over t, is going to be L over t. Why am I multiplying these two things together? Because we know that it's not for sure that Homer will end up in an accident. So it's not like he for sure loses L every time he chooses to speed up a bit. No, he loses L probabilistically. So what we need to appeal here to is the concept of mathematical expectation. Do not worry if you have not encountered it before. I think some of you might, and some of you may not have encountered it. The idea here is that we don't know for sure whether Homer will end up in an accident. But if we repeated this sort of thought experiment many, many, many times, then on average, P% of time, Homer would end up in an accident. And so in that proportion of times, he would lose L. Therefore, on average, he loses the amount P times L, which in our case is L over T, since we assume that P is equal to 1 over T. Excellent. So we've built some assumptions of our model. We've described the trade-off. Now, you may want to ask me, but what does it have to do with the seatbelts, if anything? We need to think about how to incorporate the idea of the introducing the seatbelts into our model. So let me ask you to answer a second poll now. Let's think about what is a good way to think about what seatbelts do in our model. Possibility A is they reduce T. Possibility B is they increase B. Possibility C is they reduce L. And possibility D is they going to set P equals to 0. To remind you what these letters mean, we have this note on top with all the notation. So Ellie, if you wouldn't mind putting the second poll up, please go ahead and vote what you think is going to be the effect of seatbelts. Good, I'm seeing some good answers here.
I'll give another 10 seconds to the last couple of you if you haven't put in a choice.
Excellent. I'm very pleased with this because the vast majority of people answered the question correctly. The correct answer was indeed they seatbelts lowers L because they make it less likely that one would die from an accident. And therefore they lower the damage that Homer faces should he have an accident. Notice that A doesn't work because T here, the time spent traveling, is the variable that Homer chooses. It's the variable under his control. And seatbelts don't really affect how long we take to drive from one place to another. B doesn't work either, because B is the benefit he gets from the coffee and the newspaper. So seatbelts are not relevant for that. D doesn't work, even though it's somewhat tempting maybe to say D, because the seatbelts don't actually affect the probability that we have an accident. Our driving is the thing that affects that probability. So excellent. Seatbelts reduce L here. So in order now to analyze what our seatbelts policy will do, let's think about how Homer is going to make a decision about how fast to drive, or in other words, how to choose T, the time he spends driving. Now, economists think of people as weighing up costs and benefits of something when they're making a decision. How do we capture this in a mathematical form? We're going to introduce something that economists call utility, but it's really a bit of jargon that is easier to understand if we just think of it as the difference between the benefits. These are the benefits, and the costs of T, the ones that we have identified earlier. So we've defined them earlier. All we've done now is found the difference between the two. How are we going to think about Homer choosing the T here, the time he spends driving? Well, we're going to assume that Homer is going to try to maximize his net benefit. So he's going to maximize the difference between the benefits and the costs. He wants to choose T such that he gets the maximum net benefit. How are we going to do this mathematically? Well, and here, some of you may be familiar with the mathematics of what I'm about to show. Others may not be familiar. Do not worry if you haven't seen this before. Hopefully, it will be quite intuitive. What we've got here with you is a utility function. If we plotted it, so if I plot U on the vertical axis and T that Homer chooses on the horizontal axis, it's going to look something like this. What we're looking for is a T at this maximum point. So this is the T that's going to give Homer the maximum net benefit. How do we do this? We'll notice something about the slope of the function at the point T star. It is flat. Oops. So if I was to draw a tangent at this point, it's just going to be a flat line. At the maximum, the tangent is going to be 0. So that's how we're going to find the T, which maximizes Homer's net benefit. We're going to differentiate this utility function. This is me taking a partial derivative, but actually it's only a function of one variable. Everything else is fixed. So I might as well take a normal derivative. It doesn't really matter. I'm going to take a derivative with respect to T because that's the variable that Homer is choosing. And then I'm going to set it equal to 0. Right? Excellent. So differentiating this with respect to T is going to give me minus B plus L over T squared. right? I'm doing this quite fast, but I know that most of you will be familiar with the differentiation. And so this is just a straightforward application of differentiation rules. Don't worry if this is not entirely clear. You can go back to this later and just double check that it all works. So now what I want to do is to solve this equation for t, the t that Homer would choose. And if I do that, I'm going to get that t is equal to square root of the ratio L over B. So this is the optimal time that Homer will choose to drive. It depends on two variables, L and B. Does the relationship make sense? Notice that when B is higher, T is lower. So the more, remember, B is the benefit that Homer derives from his latte and his newspaper. So the more benefit he derives from that, the less time he wants to spend traveling. So it makes sense that when B is high, T is lower. The opposite is true about L, because remember, L is the loss from the accident. So the bigger is the potential loss that Homer faces if he has an accident, the more carefully he is going to drive, and so the longer he's going to spend on the road. So there is a positive relationship between L and T. Excellent. Let's now we've derived how Homer actually chooses T, we can think about the seatbelt effect. So remember, we said with you that seatbelts lower L. And the probability of the accident is falling in T, the time that Homer spends on the road. Moreover, we found just now that T is equal to square root of L over B. So what happens when L goes down? So the seat belts are introduced. When L goes down, because of this formula that we've derived with you, time spent on the road goes down as well. Just like we said, because Homer is less careful now. He knows that the loss from the accident is not going to be that large, so he is less careful. He wants to get to his latte and the newspaper faster. As a result, because P is an increasing function, is a falling function of T, the probability of an accident goes up. So we've just shown with you that introduction of seatbelts increases the probability of accidents or increases the accident rate. We've managed to build a model from which we derived the initial intuition that we talked about. Because people are less careful, they drive faster, the probability of an accident will go up. Now, remember, original predictions in those Congress and Senate bills that we talked about were not about the probability of the accident, they were about the death rates. So let's think about what is the effect of the seat belts on the death rate in our model, given that we've discovered that seat belts increase the probability of an accident. So what would be the, what does our model say? What does our model show will be the effect of introducing seat belts on death rates? So we have three options: negative, positive, or could go either way.
I'll give you 10 more seconds.
Excellent. So again, I'm really pleased to see that the majority of people chose the right answer here. It is C. The effect on the death rates is ambiguous here. It can go either way. Why is that? Because within our model, we showed that the probability of an accident goes up. So the number of accidents is going to rise. But the engineers are right as well, because in each of these accidents, it's less likely that the person will die because of the seatbelts. So we don't know overall which way the product will go. It may be that the fact that people are less likely to die in each particular accident outweighs the fact that the probability is rising, or it could be the other way around, or it could be, as in American reality, that the two effects actually offset each other almost exactly. And that's why we have seen no effect on the death rates in the American data. Good. We've now built a very simple model with you. If we wanted to, we could extend our model to model some additional effects, not just effects on death rates, but make some other predictions. For example, our model would predict that the pedestrian injury rates should go up as a result of introduction of seatbelts. Why is that? Because the number of accidents is going up, but pedestrians are not wearing seatbelts. So for them, there is no positive effect of the seatbelts. It's all negative news for them. The same thing is true about property damage. Our simple model says introduction of seatbelts is going to cause more property damage, because also seatbelts do not help property. But the probability of an accident of somebody running into a shop window is going up because people are driving more recklessly here. And in fact, what's interesting is if you look at the US data, both of these predictions have been borne out by reality. Both pedestrian injuries and property damage went up after the 1966 Act. Right, guys. So we managed to build our own little model of behavior and explain some really puzzling facts in the data. What do we learn from this overall? Well, not that we should ignore seatbelts, right? I don't want you guys to take this message home. Seatbelts are very important. What we learn from this is that people respond to policies by changing behavior. And this is very important for policymakers to keep in mind when they introduce new policies. This is often known in the policy literature as unintended consequences of policies. Obviously, when people were introducing seatbelts in the US and the UK, nobody really wanted people to drive more recklessly. But that was one of the consequences of the introduction of seatbelts. And we need to be really aware of this. And what it also tells us is that modeling is extremely important for understanding and predicting outcomes of policy. Right. So this brings me naturally to my conclusion. It's been great fun. We've built a little model with you. We've explained some pretty interesting facts that people have not predicted in advance. And we've drawn some overall policy lessons. Thank you very much, guys, for coming. And if you have any questions, Ellie, it's possible to open the floor, right?
Yes. So thank you, Julia. I found that really interesting myself. But yes, thank you. If you do have any questions for Julia now, we do have a bit of time. So I guess whether that's on the talk that she's given, but also I guess around economics as well, then please do put them into the chat or the Q&A. I'm happy to field both and read them out. So we'll just give you a minute or so if you are typing. I know that it's not super quick, but if you do have any, do ask them now. Okay, so we've got one question here. How maths-based is economics at Cambridge?
It is quite strongly math-based, yes. So today, what we did today would be kind of an example of what students might be doing in their first year at Cambridge. What we tell people when they apply for admissions is that you need to combine very much two qualities. You need to be very good at maths so that you don't really have to think about maths when you're doing it. Because what we want you to think about is human behavior. So you have to be good at maths so that maths is on autopilot. And then you can spend your time thinking about interesting questions about human beings.
Great. And this is also, you know, all of you are doing maths and further maths A level or an equivalent in your system. So this really sets you up very well for a maths-based course like this. Someone else has asked, could this example be part of moral hazard?
Absolutely, absolutely. I'm very pleased that somebody knows. Economics is full of various sort of buzzwords and little pieces of jargon, but moral hazard is indeed what this was example of. We see this all the time. For example, so the phrase itself is very strange, right? It doesn't really do what it says on the tin at all. So what does it mean? It means a situation where the person changes their behavior as a result of being subjected to some sort of a contract or a policy. A very usual example of moral hazard is insurance. Once people take out insurance, they become less careful, riskier in their behavior. Another example of moral hazard is why, when we have banking crisis, the central banks are really reluctant to bail out banks, because they're very worried that if they bail out banks once, next time banks will see this as an insurance, and so stop being prudent, will increase their risks in the expectations that they will be bailed out. So thank you.
We've got another one. Is economics more about the maths or applying maths to human behavior and tendencies?
So it's definitely about the latter. We're not really interested in maths for maths' sake. Sometimes we sort of say jokingly that economists have a bit of physics envy, in the sense that we also use mathematics as means to explain the real world. But the physicists are concerned with the matter, and we're concerned with the human beings, which are so much more interesting.
How similar is economics at university to the sort of things that we cover at A level?
Not very similar at all. So to the extent that, as you might know, that we don't actually require economics A level for admission to economics degree. And the reason is because you pretty much learn things here from scratch, partly because it is very mathematical. So you start with a completely different way of looking at things. Having said all this, sometimes people would ask me, so is it pointless to take economics A level? The answer to that is no, because it gives you a taste for the kind of questions that economists find interesting. So you can ascertain yourself whether this is something you might be interested in, but keep in mind that you would notch up the rigor quite a lot because we use mathematical models.
Okay, I'll wait if there's any more questions. I kind of had one myself. Are economists and the kind of what you've demonstrated in this talk, has that been used in the last year during the pandemic?
So there's been a lot of work on pandemic. Of it's a little bit sort of. Maybe it's a little bit cynical to say, but economists get quite excited when crisis comes along because it's usually an opportunity to study something. All sorts of economists have been very interested in the effects of pandemic. Probably the biggest topic has been the inequality that results from the pandemic, because even though it's been obviously a huge effect on everybody, there's hardly anybody in the world who's untouched by it. The effects have been really unequal, depending on various things, including initial economic situation. And this seems to be one of the biggest questions that has come out of the pandemic. There have been also other studies done. For example, we have an economist at the Faculty of Economics here, Flavia Toxvert, who's a specialist in epidemics and in transition in processes that look epidemic-like. So he's been very much involved in consultations with various policymakers on the question of transmission. There are, of course, lots of questions one could ask around behavior, particularly do people obey the regulations of the lockdown? Why and why not? For example, our students in the university have been asked to participate in a program that's called asymptomatic screening. So from the moment they arrived in October October gone by, 2020, they were asked to take an asymptomatic COVID test every week. And I'm so pleased to say that most of our students have risen to this challenge, and they've been doing this basically in order to keep the infection rates down in the university and the city as a whole. And I think it's a very interesting experiment for economists as well, because underlying this testing is almost entirely selfless behavior of students. I remember coming full circle to what is economics about. We thought that maybe it's about money when we first talked about this question, but actually a decision like this is very interesting to economists because it's altruistic, and we really want to understand what drives people's decisions when there's actually not much benefit at stake for them. It's a very important thing for the society.
Awesome, thank you. I've got another question about sort of school versus university. So is economics very similar to the statistics we do in maths, or is it more about behavior prediction and other things?
Again, I would say that statistics, just like maths, is a very useful tool, but it's a tool. So the questions we will we ask in economics here are about human behavior, and statistics just helps us find some of the answers. But definitely, if you have an opportunity, if you want to do economics and you have an opportunity to take more statistics in school, I would highly recommend that. It's one subject where I think most of our students find there is the biggest gap between what they've seen at school and what they start doing in the first year of university.
Great. We've had a question. Do fellows for economics at Cambridge move around college bases or not?
Typically not. So usually a person joins one college and they stay there for most of the time. There's some exceptions, but not as a rule.
And then I've got two final questions here. So the first one is, are there any resources that you would recommend to kind of have a go at sort of economics related questions, these sorts of things that you kind of demonstrated they found it really interesting?
So in terms of books to read, I personally think Free Economics, although not very new, is great because it shows how microeconomists can apply lessons of microeconomics almost to everything. If you're more interested in macroeconomics, This Time It's Different is a book by Rogoff and Reinhardt, and it's a tour of economic crisis around the world. And of course, the title is tongue-in-cheek because the main argument is that it's not different. It's very similar every time, but every government thinks that our case is very different from other cases. If you wanted to sort of hear more about what economists do, Oriana Bandier, who is a professor at the LSE, gave a very nice lecture for the Royal Economic Society, which is on YouTube. I think it's actually called What Economists Really Do. And it gives a lot of different examples, mostly from microeconomics, because she's like me, a microeconomist, so thinks about people rather than big picture things like crisis and inflation.
Great, thank you. And then a final question, which I think is quite interesting as well. Do you think economics might change in the coming decades, particularly in relation to climate change and the changing utility of resources such as water, land, etc.?
I think climate change poses quite a big challenge to the society, obviously. Economists have been thinking about it quite a lot. So if you're interested in this, you might be familiar with the Stern report in the UK, which some years ago tried to understand how we can think about climate change and what policy we could use. I don't think that the question itself leads to us reconsidering our approaches, because although it has some very specific challenges, it doesn't exactly require very different tools or methodology from the one that economists have been using before. I think what's very difficult in the climate change question is trying to understand how we can create policy citizens, governments, which doesn't affect just us, but will affect future generations. In fact, the biggest effect is on future generations and not us. So it's all about this altruism that we were talking about a little bit earlier. Of course, another part of it is that there's huge uncertainty about what's going to happen. And this is really about choice under uncertainty. My feeling is that economics is changing a lot and has been changing for the last sort of couple of decades, an enormous amount. A very big source of this change is introduction of ideas from psychology into economics. This has been a huge new influence, and economists are really adapting to it very rapidly.
Brilliant. Thank you. And thank you everyone for your questions.